All right, we'll talk just for a couple of slides about resonance. For some Lewis structures, for example, this happens in the case of ozone, um, a single Lewis structure is an inadequate description of the molecule. For example, here with ozone, one could draw it either with a double bond between the central oxygen and the left oxygen, or the central oxygen and the right oxygen. So this happens pretty often when we have systems that have double or triple bonds in them. So often a single Lewis structure is an inadequate description of a molecule. It is possible to draw as many as two different Lewis structures that are good representations of the same molecule, and we call these resonance structures. And it's some blend of these two structures that is a better representation of the actual physical molecule that exists. And how we saw this right away was if we look with spectroscopy at the bond distances in this molecule, there's not a short OO bond and a long OO bond, which is what we would expect for something that had a double bond to one side and a single bond to the other. But even more interesting than that, so ozone has two identical oxygen-oxygen bonds, and those bond distances are intermediate between what we would expect for a single bond, which is about 1.48, and what we would expect for a double bond, which is 1.21. Experimentally determined distance is 1.28. And so these are, we can think of these as having a bond order of about 1.5 between each oxygen, rather than having a bond order of 1 or 2. Okay, and so if we were doing this, this has two identical resonance structures that we could draw. So very often I will ask you, I'll give you a formula and ask you to tell me how many good Lewis structures you can draw, how many good resonance structures that obey the octet rule. From organic chemistry, I'm sure you remember this happens with benzene. So I could draw benzene with the double bonds here, here, and here, or I could draw benzene with the double bonds here, here, and here. Same sort of deal happens. These carbon-carbon bond distances are intermediate between what we would expect in a carbon-carbon single bond and a carbon-carbon double bond. And often in organic chemistry, and I'll do this quite often when I draw these also, we'll actually represent the molecule like this. And this circle is to remind us that it's a delocalized representation, which is a blend of these two resonance structures. Okay, benzene's carbon-carbon bond distance is 140 picometers. That's less than a carbon-carbon single bond at 154 picometers, but more than a carbon-carbon double bond at 133 picometers. And here's what we're trying to do. This is a Whelan's analogy for resonance structures, is if we never in our lives had seen a rhinoceros, but from mythology we knew what a dragon was, and we knew what a unicorn was, we might describe the rhinoceros as a blend of a dinosaur and a unicorn. And what's really good about this Whelan's analogy is people have the propensity to think of these as flipping back and forth, and that's not what's happening at all. It's not rapidly jumping between resonance structure 1 and resonance structure 2. The real structure is truly a blend, in the way that our rhinoceros is not popping back and forth between being a dragon and being a unicorn. We're trying to describe this real physical object with two different mental constructs that we've come up with. It's got rough skin like a dragon, kind of a dragon looking face, and it has a horn on its head the way that a unicorn does.